Hello. Hello and hi again. We are talking about Kafka and RabbitMQ today. And let me share with you guys how it started. A kind soul on our Slack suggested we do an episode on the distributed task queue, which is a good, interesting question. It appears in multiple broader settings, both real life and interviews. So I figured, yeah, let's record a 45 minutes episode on how to do distributed task queues. And then during preparation, and after some people were kind enough to help me review the slides, it turns out it's a big problem that is really complex. So in the spirit of keeping this educational, hopefully it's going to be useful enough, valuable enough for you guys and others who are watching it, thank you. We decided we're going to split this episode into two. We're gonna touch on the distributed task queue towards the end. I would say maybe 15-20 minutes. Maybe even 25-30 because it's a big topic. But I'm gonna, for the distributed task queue part, I'm going to only touch on the function requirements, non-function requirements, and how to begin approaching the problem. The actual solution would be in some of the next episodes, hopefully the immediately next one. What we will cover today is what are the message queues internally in your system designs, what are the different flavors, how to compare them, how to choose the right one, and what should the system architect and what should the interviewing candidate in 2022 know about message queues out there. Here's the plot. I generally start from fundamentals. I think it's a good idea. So I'll spend some time talking about the message queue itself as the data crunching, data processing primitive. Again, thanks for you guys in Slack suggesting me that I should cover what the producer consumer pattern is. It's surprisingly well fit, well designed for this particular episode, so I should talk about that. And I'll give you guys some examples on how to tackle seemingly hard problems. Not how to tackle them, I'll give you guys some example on how these problems emerged 30, 40 years ago, and they have been solved in different ways, many of which made it today into the primitives you would use in the cloud. But the problem is there for quite some time, and software architects and developers have learned how to deal with it in multiple clever ways. After this fundamentals intro part, we'll talk about distributed and cloud message queues, because I still firmly believe that system design is the art of system design is largely about how to build systems so that the sum is greater than the parts. So we can stack standard components together and end up with something bigger. And understanding how exactly do you get big out of the smalls, is what I think the key to system design in general and to using message queues in particular. And much like with SQL and NoSQL, in message queues there's no single dichotomy, there's no single dimension along which you can compare the solutions. Nonetheless, it quickly boils down to Rabbit versus Kafka, and this is technically a big enough topic, which I ultimately decided to make the title, the caption of this episode, even though I hope it's going to cover more than this single dichotomy. And then we will enter the next episode. As I said before, we'll just cover the function requirements of this kind of distributed task queue problem. I'll talk a little bit about where it pops out, because it's surprisingly widespread, and I'll walk through some standard pieces where people generally get lost, make mistakes, or otherwise I believe are not thinking from the best starting points, which is exactly where I can help. Previously, we recorded a couple of things that are surprisingly relevant. Specifically, there are 3 episodes, and I'm going to paste the links later. Somehow YouTube thinks I'm not interested enough in making money, and I don't have a partner account, so it's not going to be possible for me to put these boxes on YouTube so that you can click on them. So I've done it like this with a picture, and I'm gonna share all these links in the first comment, I guess, as well. So basically, we had an episode quite recently on DBs and OLTPs. I didn't want to call it SQL versus NoSQL, but it largely is about different applicability areas of different databases, and that episode contains plenty of references as to what these multiple dimensions of comparison between SQL and NoSQL are. I personally find the dimensions of comparison between different message queues to be quite similar, so I think you will do well referring there as well. And then slightly over half a year ago, so the content is was of slightly lower quality and the recordings are not as good, but we had 2 episodes. One is specifically about Kafka, thanks Antonio for talking about it, and there was one episode about exactly once as the message delivery guarantee, which also somewhat does relate to this episode. First time so far, I'm referring to all the episodes. I guess we are growing. All right, fundamentals. So before we talk about message queues from the system design perspective, it should be mentioned that there is a paradigm in software architecture and software design called producer-consumer. It's a really simple idea that the part of the code or the part of the system that creates a task, that is the originator of a certain job to be done, is not the same as the part which actually executes this task. And I want to stress that this paradigm made a lot of sense far before we had clouds or distributed systems as we understand them today. This problem was there since, I think, at least the 70s. And I'm not qualified enough to talk about what happened in the 70s, but I can, maybe in the 80s, but I can tell you confidently that in the late 80s and through all the 90s, the way systems were built, think of a database. Think of a standard database. It doesn't really matter if it's a SQL one or if it's an RDBMS or a NoSQL database. The term didn't exist before, but who cares? So you want to update some data points, some row, and you have multiple columns in which you have indexes. In order for this transaction to execute, to commit, in order for it to be reflected in the state of the data, a lot of things should happen. You write it to write a headlog, just in case everything crashes, you can still replay it. You change the record of memory, you have to update certain indexes, and concurrently, potentially concurrently with updating the indexes, you need to write the updated record itself to the file system. If it's a B tree, you need to rewrite the root or whatnot. Tons of work to be done. You could parallelize this job. And back in the late 90s, it was certainly multi-threaded, even the early 90s too. But in the 80s, it was a single-threaded processor, central processing unit, CPU, which could have interrupts on disk write succeeded. And it's effectively the same as you would design it today in JavaScript, where the single thread is executing all the tasks, where your synchronization primitive is a function. So technically, this idea of using internal message queues was alive and well back in the 80s or even before. Today, even if you don't build effective real-time systems, chances are you have heard about thread pools. Chances are you have heard about log-free queues. So it's all making sense in many ways. I just do want to emphasize that this problem space has been there for a while. In fact, OOP, object-oriented programming, we view it today as mostly this encapsulation, polymorphism, inheritance, but it's a hijacked term. OOP originally was meant to be the paradigm where objects talk to each other with messages, so that every object, think of every class instance you have in your code, has an incoming message queue. And instead of calling synchronous methods, you send a message and you asynchronously expect some result. It just so happened we can build better systems, and it's easy for humans to reason about them, and it's easier for compiler developers to optimize the code. If we walk away from this paradigm in favor of the current, mostly imperative structures, I had to say this. I think this is the right framing for the next steps. Now, again, still in the fundamentals phase, it's important to understand, I think, that queues are always faster than key value stores. Forget indexes, forget databases. Let's say you just need to change values for keys. You can think of a file system where you just change the contents of a file. That's a simple database, simple key value store. If you want to change 100 random keys, chances are you would have to put this into 100 random places. Okay, that's the case with B trees and databases. In the modern world, we are mostly conversion to LSM trees, so you would not change it in 100 places on disk. But still, you would need to write these 100 things independently, and then eventually compact this squash, this LSM tree log. at the same time, the queue, which is first in, first out by design, is just appending records. You can think of them as text file rows, text file lines to a file, which is a super simple and fast operation. So intuitively, it just makes a lot of sense that if the task you're solving internally in your system, if a part of this task can be handled by an append-only file that you write and then concurrently read, or maybe read from memory, and then you rotate these files if they're in the file system, this should be faster than database transactions. And assuming you only append to a file and assuming your hard disk is configured properly, this gives you a solid enough guarantee that the data would not be corrupted because it's append-only. If it's on disk, it's append-only files which you rotate as log rotation, tons of standard techniques. If it's in memory, another famous technique to use is the circle buffer, also known as ring buffer. I wouldn't go too much into these implementations, but it's such a simple idea. You allocate a fixed block of memory and you just rewrite left to right and then left to right. And as long as you don't write more data, as long as the active, you have like a head and a tail pointers. Head moves when you write data and the tail moves as you process this data, so you can overwrite it. As long as the total amount of data you store is less than this circular buffer, is this ring buffer, all the overwrites still overwrite the data you never ever would need again. So it's a wonderful simple pattern. Can be built log free too. It also handles, like spoiler alert, it also handles back pressure natively, because if your queue can only handle, let's say, a megabyte of data, if suddenly you're processing tasks, threads, processes, or whatnot, if suddenly they're behind, you would just reject publishing new records to this queue, or you would wait until, like, you would reject as in return a failure or an exception, or you would wait until the consuming side has freed some space in the queue so you can insert new records. So all this more and talk about back pressure, which is a big topic in cloud architecture, is surprisingly simple. Your queue, if you assume your queue can grow infinitely, chances are you have missed some potential failure modes of your system. At the very least, you would pay more money to Amazon or whatever provider you're using, or your disk is full. In the worst case, you have some logical flaws in your design, which are worth thinking about. And yes, the second spoiler alert is Kafka indeed is a bunch of append-only. I like to call them log files. I believe Kafka does call them log files. I'm not sure the term applies, but it is a bunch of append-only immutable files, which contains these sequential messages which you can later read and replay. I think I'm done with the fundamentals. Any questions here? Okay, hope it was useful. Now, if there's one thing you remember from this episode, I suggest it to be the following. Much like with the SQL versus NoSQL dichotomy, you can compare different message queue solutions along a single dimension. And I'll explain soon why. These are just the 4 questions I think that should be asked. And again, for each of 16 options to answer yes, no, I can think of a custom solution that would be far superior to any standard solution, given some artificially created problem statement. So choose carefully. I try to order these dichotomies, these dimensions, these questions in some reasonable way. I'm not sure I succeeded, but just treat them as 4 independent questions. The first I would ask is, do we need to persist the data so that we can replayably, so that we can consistently replay it? I was looking for the word. Perfect replayability is when you can redo the same operations on the same queue later on, like years from now, and expect to get the same result. It's a different conversation. Like, you shouldn't use random number generators. You shouldn't use local host time. But it's really good if you need to replay your data. It's really good that it's never inconsistent. So logically speaking, you have some beginning of time where you start writing your log here, and from the beginning of time to a certain timestamp or offset of the message, this is a full description of what your data should contain. You can think of it as a database replication log, logically, but technically, if you want replayability, that's a standard to aim at. The second question that is kind of related but not 100% the same is, do you care much about the order of messages? If the client sends A and then B, do you expect the listener, the subscriber, the consumer words matter? Do you expect the other side to get A and then B? This is a surprisingly difficult problem. Moving ahead a bit of myself, if you can guarantee it at scale, you have solved the total order broadcast problem, which is identical to the distributed consensus problem. So it's really hard to do it well. You pretty much have to reinvent console or replace console by something better. You pretty much have to reinvent or rebuild Paxos or Raft and implement it yourself, which is an extremely hard problem, technically unsolvable under real-life constraints with any reasonable precision. It can be solved in practice, and it is solved in practice, of course. Just keep in mind that if you want total order of messages to be exactly the same when you replay the data later on, 10 years from now, that's really hard. In practice, in Kafka, again going ahead of myself, single topic, single partition guarantees the order to be fixed. Once you have multiple topics, they can be totally out of sync. And once you have multiple partitions of a topic, within the same partition, the order is guaranteed. Across partitions, bad things can happen. So you need vector clocks. Potentially tricky topic. Causality is one of the biggest research areas, I think, in this field. I will not go there today because A, I'm not an expert. B, it's meant to be an educational episode. So the third question I would ask myself is, do you need custom message routing logic? If you can afford to have a single topic, single partition, if the data volume allows for that, if the requirements fit for that, you could just use a single topic, single partition Kafka, or any other solution, to be honest. In terms of any other solution that supports persistence and replayability, you'll be good to go. There's this thing called AMQP, or AMQP, I always mispronounce it. It's the standard open protocol for intelligent subscription to the message broker, where you largely outsource the message routing, message retry, and all this logic. You outsource it to the broker itself. So your business logic can only focus on executing the tasks, the actions based on the messages they receive. If you need that, you would either have to build it yourself or use the message queue solution available out there that is not designed for persistence and replayability, but rather for this dimension. So in my head, custom message routing is kind of the other end of the spectrum for the first two, but I still stress it's not a single dimension. It's not a single dichotomy. And a huge painful topic is message acknowledgements and message retries. It has to do with exactly once processing. It has to do with guarantees on the writer and on the reader. It has to do with can multiple machines get the same message at the same time, or at different times if one machine died. It's a huge painful topic. It kinda is non-existent if you can afford your message consumption patterns to be replayable and ordered at all the times. But in that case, you just use Kafka and you're happy. If you cannot afford this guarantee as a business requirement, you have to think for yourself, how do you handle these corner cases? Practically, whether we like it or not, this choice often boils down to just choosing between Rabbit and Kafka. Kafka is a standard solution to process all the data sequentially, replayably, and Rabbit it's by far not the only or the most powerful, it's just most commonly cited and most commonly referred to message broker that supports this AMQP protocol more or less effectively out of the box. And in the real life, if none works independently, which often is the case, spoiler alert, it is the case for the problem of the distributed task queue, which sparked this episode. Once you cannot easily fit your problem space into one of these two boxes, you would have to experiment, innovate. If you can afford to use multiple queues for different purposes and build a large system of simpler components, good for you. If you're lucky, if you cannot afford it, at least be aware that these two primitives, Kafka and Rabbit, exist and are pretty mature out there. So chances are, if you want to build your own broker, you could at least leverage something, such as persistence and replayability from Kafka and the AMQP routing rules from Rabbit. Okay, moving on to Rabbit. So Rabbit is effectively what enables you to leverage the AMQP protocol. One of the mottos which I really like is smart broker, dumb consumer. To me, let me do a small detour here. To me, one of the aspects of system design is how to properly apply divide and conquer in designing different parts of the system. Because fundamentally, you're not just writing code. You're building a system of different teams, different people. Some of them would leave in the next 5 years. Your code has to be maintainable at all. So take, as an example I often use, take Nginx. There's nothing inherently novel that Nginx does. If you're writing a large application in Java, in Go, in C++, and Rust, you can build it so that you don't need Nginx at all. But the beauty of Nginx is not just that it just makes certain things slightly faster if you cache things correctly and route them dynamically. The beauty of Nginx is that you can intelligently split the work between the software developers and the DevOps admins who would run this code. They can load balance, they can route ports, they can add instances if they need, and the end user who talks to your service from the outside would just hit an endpoint or load balance multiple endpoints, load balanced by a load balancer, and all these nodes would route the request to the right places. So there's nothing inherently essential in Nginx, except it just happens to be the product that is extremely well designed to act as this demarcation social teams proxy between the developers and the DevOps. If you need this kind of proxy between tasks creation and tasks execution, AMQP offers that. So if a big part of your business problem for which you're considering a message queue or a message broker has to do with message routing policies, and if you know that these message routing policies, as well as routing, acknowledgements, confirmations, retransmissions, fan-outs, if that's a big part of your business logic, consider outsourcing this to AMQP, which means to Rabbit, because this may well be the best design you can think of, as it allows your developers to just build their own small task executors, and the routing rules could be handled by Rabbit, which can be configured by other people dynamically. The example I often use here is, imagine you have a task queue, of course, again, and some tasks are tagged as I need machines with more RAM to run these tasks. So naturally, you would have routing rules that tasks that are tagged with this marker should only go to the machines that are tagged with I have more RAM. Makes perfect sense. And now suddenly, of course, there's a retry policy, so if a task fails and then fails again, maybe it needs more RAM. So you may have a retry policy that, if the task failed twice, try it for the third time on a machine with more RAM. And then you notice that certain kind of tasks always fails unless they run on the machine with more RAM. So the natural fix is to say, this new task added last week always fails twice before being run successfully on a machine with more RAM. If you use AMQP, if you use Rabbit, you can fix this without touching any code. You just change the routing rules on a live system. And with zero downtime from all the task requests from now on, if they are tagged with this new task type, these tasks will be routed by the machines that have more RAM. And it's a beautiful explanation. I know it's a rather synthetic example, but it's a beautiful explanation of why the business logic separation between application code and message routing is really good to separate these two, so that different teams can fix different things while the other team is sleeping. Hope it made sense. Where I would suggest not trying to rely on Rabbit is, so technically I use the terms durable persistence here. I'm aware of one company, for the record, and I've spoken with a few people who do use Rabbit for reliable persistence, and they're happy with it. I don't have a good answer to the question of why is it not a good idea. It might be a good idea. I just know that when you need durable persistence, Kafka is just so much more reliable, just because of the way it's designed. And I don't think I can have a short, good answer to explain this, but I hope after this episode you would have the same impression, because it follows directly from the first principles, from the way they are built from the ground up. So if you need durable persistence, if you need message ordering guarantees and replayability, probably you don't want to use Rabbit. It's just not designed for that. Also, if message routing is simple, and you can expect it to not change over time. If your message routing rules can change over time dynamically, and if you can lose messages or double process them, that's just a perfect use case for Rabbit. It's a lot harder to design this. It's a lot harder to use Kafka in this use case. But the message routing rules are super simple, and if you know that the fundamental nature of your business is that these rules will not change, then you probably don't need to rely on Rabbit for this, and you might as well hard-code it, or use Kafka if they fit Kafka, or hard-code some routing rules in simple routers, load balancers, or whatnot. There will be stateless components on your side, which are super easy to maintain, and they hardly fail to begin with. Small step back towards fundamentals. Again, I like those. Rabbit is based on Erlang. Erlang is a really interesting programming language. Honestly, it's more than a modern programming language. It's the language, it's the virtual machine, and it's used for. It was used in the telecom industry to route not just network packets, but I think phone calls and stuff. I'm not an expert here, but I know that's a huge part of Erlang. Erlang is what you would get, the Erlang's virtual machine, I would say. You don't have to use Erlang as a language. There's Elixir, which is still compiled into Erlang VM, but it's a language that looks a lot more like Ruby. But Erlang VM is a genius piece of design. It's what you would get if you would try to design a system where the threads, the execution threads, are so lightweight that you can pretty much have every single request. You can assign every single request its own thread. So it's a language designed for billions of contexts concurrently existing in memory. They're all event-based, and when something happens, some contexts change their state. Because it's designed this way, it's distributed by design, because you can always add more machines, and they would acquire some of these contexts and handle those. And another amazing property of this design is that you can change the code with zero downtime by design. There's no restart, because each living entity, each living thread has its own state. This state has the version of code, if you wish, attached to it, and it would continue execution with this version of code. So it's an ingenious piece of work. It's extremely good for certain cases, and you can think of Rabbit or even AMQP, to be honest. It's one of the prime examples of what Erlang is good at. Again, naturally to me, from this it follows immediately that in terms of order and guarantees of messages and in terms of persistence, Kafka that just writes files entry after entry would be more effective and more reliable. And also Kafka has leader elections to reliably persist data in multiple places. But fundamentally, if you do want to have this magic box that somehow works, and you can add more machines, and it works slightly better or handle more data, that's what Rabbit is designed for. Of course, Rabbit can handle more messages than fit in memory, so it has some workaround mechanisms. Again, I have not used them. I'm not an expert. But if your data does fit in memory, which honestly is not too hard these days, memory is kind of cheap, then Rabbit can do miracles for you. And now we get to Kafka. Kafka is the biggest player as long as you need replayability. But it really rocks if you cannot lose messages. If you need to not lose messages and you need to keep them in certain order, again, single topic, single partition, order guaranteed, across topics, across partitions, vector clocks are needed because things can get dicey. But if you need the messages to not be lost and you need to guarantee them their order in some way, Kafka does this really, really well. So yeah, as I said before, in terms of guarantees offered when it comes to persistence, Kafka beats Rabbit any day. Just due to the nature of how Kafka is designed. You configure exactly how many nodes should confirm the message as it's being published. If you need strict guarantees, like when I build secure REST event sourcing systems, I would say use 5 or 7 nodes for Kafka, different availability zones, and only confirm the message to the producer, to whoever writes the message, after it has reached, I don't know, all but one of these nodes. This gives you the guarantee that if more than one node fails, the message is still there, as long as the writer of the message received the confirmation. Kafka saves messages to disk quickly enough. It's not like best effort. Eventually, I'm going to flush it to disk. It does write to disk soon enough because it's designed to be replayable. For performance and for durability, Kafka has leader elections if you have multiple nodes. So behind the scenes, if one node dies, the other one becomes the leader. As the user, you don't need to know this, but to me, it's it's offering me some peace of mind compared to Rabbit, where there's a big mass of events floating around along this many-to-many graph. In terms of Kafka, I know for a fact there's going to be a single thread of a single machine writing a single append-only file, and as long as everything's working fine, which is the case most of the time, if I send 2 messages, they're going to be in this file one after the other. And what is also really important, it follows naturally from the fact that Kafka has literal actions, so it has some durable persistent store. It used to do it in Zookeeper, I think starting sometime last year. Kafka no longer requires Zookeeper, it has its own rough protocol. So to me it follows naturally. I'm not sure if it's natural as an explanation. That because you have this storage that is durable, Kafka offers a wonderful guarantee that if you want to consume the messages one after the other, Kafka can store your offset up to which have you processed the messages and confirmed them. Which it's not a big deal on a large system, but if you just want to simplify your design, you can build a small stateless zero database black box, which will just subscribe to a Kafka topic to consume it. And this black box will just get a message, process it, confirm it, get the next message. You would get them in bulks, of course, and most likely confirm in bulks. That's a different topic about confirming asynchronously or synchronously. But the point is, if you just need to process the messages one after another, you just outsource this offset tracking to Kafka, and you know that if your machine dies and goes back up, it's going to resume from the message Kafka's going to send you the messages starting from the first one you did not confirm. And of course, you will process them in order because that's what Kafka is: append-only, immutable logs. When to look to the solutions other than Kafka? First of all, my favorite example here, if the message subscription, or rather consumption for Kafka, if the message consumption rules are such that when you add machines, they should take messages away from other machines. So the other machines should not receive these messages somehow. It's a big topic, how can you possibly do it? But the idea is that if you use Kafka, you have to process messages one by one. If you were to skip some messages, there would have to be some external component that says this message, even if you see it, it's not yours. Somebody else has taken it. That's custom logic, which you have to use in multiple places, including most likely the very problem of the distributed task queue. But again, if you need to extract the message from the queue, it's just impossible in Kafka, period, because it's a mutable append only. You cannot rewrite it, you cannot erase it by design. So if you need some other kind of fundamental logic, chances are you should not use Kafka, at least not for this part of your business logic. The related topic is that if you don't process data in the first in, first out fashion, Kafka would the design of Kafka that ensures first in, first out would become a liability for you. It's a burden, not a benefit. So again, if you're in this realm, consider something else. Putting a Rabbit router message broker after Kafka is one of the subscribers, one of the consumers, is a good practice in many cases, but choose wisely. Hopefully by the end of this episode you'll be equipped with all the knowledge to choose wisely. And yeah, the routing rules. Kafka is primarily topic-based routing, so in many real-life designs you can get away with having different topics so that the topic name and ID and whatnot encodes all the data regarding where should you send it. It's not always possible, unfortunately. And I've seen designs where you have hundreds of topics and the same message goes into multiple topics, because that's the cheapest solution to emulate some sort of routing. And then the nodes, of course, will see the message multiple times and they agree between themselves. Oh, I've seen this message before, I've seen this ID, I'm not going to do it, I'm not going to process it. If you need custom logic, well, if you just need topics, Kafka might be okay. If you need topics plus first in, first out. If you need topics plus some easy, simple, basic, let's say bit mask filtering on a small number of bits, you can get clever with duplicating messages across multiple topics. There are some aggregates. If you need something else, like fanouts, like remove messages from the queue, like rerouting them to different workers, Kafka would not work. Look somewhere else.
Dima, I have a question. Hello, can you hear me?
Yeah, go ahead.
Yeah. So you said that for requirements where FIFO is a burden instead of a benefit, the first thing, can you talk about a real life example where this is the case? And even if that is the case, would it take away the core aspects of it being a queue and the simplicity that comes with the queue and turn it into some other data structure altogether? So would uh, the benefits of queue still remain if FIFO is not a benefit at all?
That's a really big question and a really good one. Uh, I have to preface my answer with a disclaimer. I like to say that all of us have biases. We can be aware of our biases, but we can't fully exercise, fully entertain the degree to which we are biased. So I acknowledge I'm biased towards consistent systems. Period. That's a fun fact about me. So I honestly think that if a system can be built in a FIFO way, you should do it the FIFO way. Replayability is best to have. So I'm this event source and event store guy who builds things this way. Mm. FIFO may not be the best idea if some tasks can be delayed or have priorities or rescheduled for later, like a priority queue. That's one easiest example, I think. The moment you have a priority queue, FIFO is not the way to do it. Yes, people can get away with it with a fixed number of priorities and different Kafka topics per priority, but still, that's hacky. The most famous, the most painful, to be honest, real life example where FIFO kills you is I've seen this multiple times at different places, and at least one of them I was involved directly, which was really hard to architect around. Imagine you have the data crunching job that processes events one after the other. If it dies, it has to resume from some offset. But maybe some important data bit is so important that if you don't process it fully, you need to resume from that bit. And to fully process it, you need to access events from the future. So in the perfect world, you would accept all messages, but this one marker, until everything related to this marker is fully processed. And Kafka doesn't let you do it. Kafka only stores the offset for you. If only you could store offset plus a few indexes. Oh, hey, this one was not confirmed yet. So that if you die and start again up, you start from your offset, maybe, or maybe from that older marker, but at least you know that the marker is still there and you haven't confirmed it. Maybe more markers have been added for the duration of your downtime while you've been down. The moment you have this kind of use case, you have to design something artificially, and no Rabbit does not help here. It will be some external data set, external database where you can keep the track record of which messages have you deliberately not confirm on time. So with Kafka, you probably confirm the message, but before that, you would write it into your own data store. Hey, I have not done processing this. It's confirmed for Kafka because I can crunch further, but it's not confirmed for my own business logic, for your own high availability reasons. Does it explain it?
Yeah.
Good question. Thank you. Yeah, it's an open topic, by the way. When you have same topic, multiple partitions, so you have vector clocks. Kafka was originally designed for cross data center database application, from what I know. And if one topic is not enough, you just use multiple topics naturally. And the most painful topic in using Kafka these days at scale, when you have large volumes of data and high throughput, is causality. Causality is a huge research topic too in this area. I don't think it will be solved in a generic fashion anytime soon, although the basic ideas are there. It's simply the fact that if you have database transaction log, you could create an account for user X, for Alice, and then Alice is credited with some money. Maybe Bob sends money to Alice. It makes perfect sense if when you replay the log, you see Alice creates an account, Bob sends money to Alice. If they end up in different partitions, which would often be the case, you can see the event of Alice receiving money for a certain account before the event that this account was created. And then what can you do? You can assume the account was created, but then you may not know some metadata for this account. Maybe they should not be overdrafted, or maybe it can only accept money from Bob. So in practice, any solution that uses multiple partitions per topic with Kafka, so you would have to have vector clocks so you cannot just assume that single offset explains your state of the system. You would need to have no offsets for all these partitions, which could be out of sync. That's how partitions work. In practice, you would have some in memory or in Redis async contexts that can only be committed once you receive all the messages that this message depends on. So those messages can cause this message to be proper, to not be malformed, until you see the previous messages that this message depends on. This one is not causally ready to be processed. And that's why all sorts of bad things happen. It's not exactly related to using first in, first out, but I had to put it out there somehow. All right, thanks. Let's move on from here. Now, full disclosure, I will talk about how Kafka consumers work. I was deliberating whether it's worth the topic or worth the slide, because I'm trying to be high level here. And then I said, screw it. Even if it's Kafka specific, if I were to design a system like Kafka today, if I were to design multi-partitions, publisher and subscription consumption, I would still do it the same way. So it should be common knowledge how these things work. Besides, in my interview prep work, I often see people struggle with this, and I think it's super simple. So I thought it's a good idea to explain this in a public video. So yeah, first of all, basic disclaimers. True exactly once is impossible, because no matter how cleverly you write your code, the machine which is consuming the message can die while consuming it. Or it can die after it has processed the message, but before the confirmation was sent, or before the confirmation was has reached the message origin, the Kafka cluster itself. So if you really want exactly once, you have to be very careful. The solution here is fancy tokens, which I don't have time to talk about. Basically, if your message does not have side effects, you can assume you can always replay it and regenerate the same side effect and regenerate the same results, and they would not be received multiple times by the receiver because of idempotency. But if your message has a side effect, let's say you need to send an email at the end of the day, you can say that once you receive the message for processing, you put some token next to this message, and you can only perform external actions as long as this token is still valid. So if your machine dies or slows down because it's Java and there's garbage collection, maybe you were down for 10 minutes, the message broker declared you dead and sent the same message somewhere else. Somewhere internally in some other database, the message broker would, or the logic that routes the messages, would invalidate your fancy token and replace it by a new fancy token. So once you're done processing the message and try to send an email, you get an error message that, hey, you're no longer the owner, you're no longer the primary processor of this message. It's a very clever idea. I don't think we have time for it right now. I only wanted to emphasize that exactly once, Kafka gets real close to it. Kafka is probably as close to exactly once as you can think of, but it's impossible to do it unless you have tons of custom logic. Kafka, of course, if you're not exactly once, you are at least once or at most once. Kafka is, of course, at least once, because presumably if you need to process every message, if you process the message twice, it's painful but tolerable. If you neglect to process it, that's a big issue. Like if it's a financial audit and you forgot some transaction, that's a big problem potentially. So Kafka will keep sending you messages to consume until you have confirmed that you have processed this message. Of course, you can make your own mistakes. Like you can declare the message processed in your own code before you actually process it, or you can make a mistake that I've processed it, but there is some asynchronous threads, asynchronous contexts hanging out. So I can't really declare the message fully processed. Just in case I die and start again, those contexts will be lost. Well, there's always room for bugs. But logically, Kafka would assume you have not processed the message until you have confirmed to Kafka that this particular consumer or consuming group, I'll get there, has processed the message. Now, if you want Kafka to keep track of your offset up to which you have consumed the data, you declare your consumer part of certain consumer group. That's an ID of a consumer group. And moving forward to the lower part of the slide, there are effectively two different ways to use Kafka in terms of consumption. You can, if you want Kafka to own your offsets, you reuse consumer group IDs. You deliberately decide that you have this part of your deployment, you have this part of your business logic, part of your code, and you hardcore that this code, well, not hardcore in the code, it's going to be in the config file, of course, but you say that this particular cluster, this particular bunch of machines would turn to Kafka assuming the role of consumer group X. This is the way by which Kafka would make sure that your consumer group X would only would process messages to as close to exactly once as possible, assuming nothing dies. The other way to use Kafka is when you handle offsets directly, manually. You may want to, so Kafka is replayable, right? There of course is retention policy. Chances are you're not going to store the whole year of events in Kafka. Probably going to be a week or a month or 3 days. But you could say, hey, my crunching job can just decide to process Kafka messages from last midnight or from certain offset which I store elsewhere. You absolutely can do it. You can go to Kafka and say, please stream me the messages starting from this offset or this timestamp, I think. Or you can compute one from the other. But in order to do it, you would need to not use the same consumer group ID, because then you would mess with the offset up to which this consumer group A, I've talked about before, has confirmed to Kafka, we have processed these messages. So really, you can do clever things with consumer groups, but fundamentally it's just two different ways. Either you outsource offset tracking to Kafka, which, by the way, if it's a single topic multiple partitions, offset tracking means tracking offsets of each individual partition. So either you outsource this to Kafka and you reuse, you hard code the consumer group names, IDs or whatnot, or you ignore them and you keep the offset yourself and you just use Kafka as the event store, which has a simple interface. Give me the events from A to X or to infinity as an infinite stream. It's really that simple. And again, I was debating whether this picture belongs here. I think it does, because it's not, even though it is Kafka specific, the design is so clean and so simple. It's important for all of us to know it. If the topic is partitioned, so if it's the same, let me start from half a step back. If you have a single topic, single partition Kafka, and you rely on Kafka's offset tracking, so once you confirm the message, Kafka will not send it back to you because you have confirmed this message. Your offset is incremented by 1. If you have the single topic, single partition Kafka stream, and you have 2 machines trying to be in the same consumer group, only one can crunch the data. Otherwise, they would compete for the same offset, which makes no sense. So logically, if one topic is not enough for you, or if you need to use multiple machines for processing because one machine, the bottleneck is no longer Kafka in this case, the bottleneck is your crunching job, is your consumer group. Then you would use multiple machines in the consumer group, but you also need multiple partitions, which is painful because you get to vector clocks territory where you could potentially get these causality issues, but ignore it for now. The important part here is that if you have a topic with 4 partitions and you have multiple machines in the consumer group, they would probably they will be allocated so that each partition is only consumed by one node, one machine from your consumer group. So in this picture, which I've taken directly from the O'Reilly book, which is published online, if you have 4 topics here, then if you have a consumer group with 4 consumers, what Kafka would do is assign 1 to 1, one topic, one revert. If you have a topic with 4 partitions, one topic with 4 partitions, and you have 4 machines in the consumer group, Kafka would assign it 1 to 1 eventually. Each machine of your consumer group would be processing the respective partition of this topic. The reassignment logic within Kafka is kind of tricky, and that's where exactly once can be broken if things go wrong, but we have to ignore it for now. It's really advanced. And I'm not a Kafka expert to begin with. I just know the fundamentals, and I've seen people use it and make mistakes. So if you have 4 partitions and 4 consumers, it's 1 to 1. If you have 4 partitions and 1 consumer, it's 4 to 1, of course. If you have 4 partitions and 2 consumers, it's most likely 2 partitions would go to one consumer, 2 would go to another consumer. If you have more consumers than partitions per topic, some will be idle. And here's the next picture. So 4 to 1, simple. 4 to 2, low balanced. 4 to 4, perfect. 4 to 5, clearly, this consumer 5 will be idle. This all made a lot more sense to me when I realized the word choice matters. When we talk publish subscribe, you have a publisher and a subscriber. When we talk Kafka, we talk consumer. And consume is why I put this pacman here. When a pacman eats the dot disappears. When your consumer consumes the message, there is an implicit agreement within the whole system that this message was consumed by this consumer, and it should no longer be sent to this consumer. And consumer group is the logical entity of this each.once guarantee. Does it make sense now? Because to me it makes perfect sense. Yeah, on the terminology level, I think I should have mentioned this before. I try to refer to AMQP and Rabbit as message brokers, because brokers is what they do. Brokers is effectively routing requests, right? That's what brokers do. And I almost never use the term message broker for Kafka, even though technically per partition subscriptions can be referred to as brokerage. I always call Kafka a message bus, because it's a bus. It's a tube. The perfect illustration for Kafka is when you take a database, the standard cylinder, and put it horizontally and make it long and narrow. Rabbit, I'm not entirely sure. I would fully agree that for certain advanced AMQP Rabbit use cases, the icon of the horizontal database makes sense on a diagram. It's a lot more business logic there. All right. Reference examples. The canonical Kafka use case is analyzing financial ledgers, maybe for audit purposes. Messages order is important, exactly once is important, replayability is critical. That's a perfect textbook use case for Kafka. The best example I can think of for the perfect use case for Rabbit is imagine what you build in is moderation tools for a huge social service. YouTube comments, Facebook, Twitter, or whatnot. There's some machine learning that can flag some comments for potentially required review. Well, first of all, this machine learning has to be applied to every single comment. You have some signals, right, that on this kind of videos, this kind of people tend to leave comments that are more likely to be marked as offensive or removed. Sometimes you need to send comments on manual review, which can take days and hours and days and maybe weeks, and you might need to resend the same piece of content to different people. Or maybe your policy is this will be reviewed by 5 people, and at least 4 should say it's appropriate. And you have filtering rules for the people you send the content to review. For example, they should speak Russian. That's probably the closest you can get to where Kafka would be the worst possible choice. If you use Kafka here, you would need to build your own broker after it. If you use Kafka here, first of all, you wouldn't care about the order of messages at all. So you lose one of the biggest benefits of Kafka. And second, you would need to put your own broker after Kafka, which would effectively do exactly what you should probably use AMQP to express as the rules. That's like designing, that's like writing C++ code to validate the HTTPS certificate. That's what Nginx does for you. That's what ELB does for you on Amazon. You can do it yourself. It's just pointless for multiple reasons. You would waste your time, and you would make it harder to maintain later on by people who are not you. So if you have this problem of keeping content moderators busy, Rabbit is just a perfect illustration. I made this meme for memorization purposes. I think it's not necessarily correct per se, but I think what would be a correct statement is the following. It's the famous failure mode of design if you use UDP, but then you have to design TCP over it. So for those of you who are not familiar with the terms, UDP is the Universal Datagram Protocol, where the packets you send over the network can arrive at any order and they can be lost. TCP is where there's this concept of a window, and you're guaranteed to receive the same data in the right order or not receive it. When you download a file through HTTP is based on TCP. When you download an image of Ubuntu, it's absolutely TCP, because it cannot be tolerated if the chunks of the file are moved around, are shuffled, or split. So if some chunk in the middle is not there, the network card would hold the further pieces in its own memory, while the network driver would store it in the main memory of the machine until that missing part is there. And it's going to request on the protocol level to resend this data from the middle part. It's an ingenious protocol, extremely well designed. Some people say it was invented, not designed. I tend to agree. So that's one of the building blocks of the modern internet. With UDP, you just ignore whatever is missing, and it's on the application to re-request the data. Common examples for UDP would be like video chats. If my network is flaky, or if your network is flaky, if I lose a few frames of you, the last thing I care about is receiving those frames. We keep talking. Like I can fail to receive every third frame, But as long as the audio is consistent with no breakages and I still see you, that's perfectly fine. That's what UDP is made for. That's what TCP is horrible at, because it will just freeze everything until that last frame that was missing would be received. And the rule of thumb is that if you need TCP guarantees and you're trying to use UDP and reinvent those TCP guarantees, you're doing something really wrong. You should really, really consider using TCP, at least for this connection. So I think the rule of thumb between Rabbit and Kafka should be that if you use Rabbit and you feel you need the guarantees of Kafka, and you're starting to think, how can I leverage Rabbit to have Kafka guarantees? At this point, you should be fully aware you're doing something wrong. Like, very likely wrong, unless you really don't know what you're doing. It's not that like drop messages like in the video chat versus financial ledger audit. It's not that this dichotomy is the perfect differentiator between Rabbit and Kafka. But I would go as far as postulating that if you need to reinvent Kafka over Rabbit, use Rabbit. All right.
Hi, Dima. So just one doubt, like in the previous slide, the before slide.
The one before? This guy?
Yeah, one before, yeah. So here, like, so what is the default behavior of the Kafka? Like, so if we have multiple consumers, right? So one-to-one is the default behavior, or if one consumer wants to read all the data from the all partitions, can that happen?
That's the leftmost picture, right?
No, like if you have multiple consumers, so in that case, if one consumer wants to read all data from all partitions, so
I can answer on a high level. I think I understood the question. The high level answer is that it's an advanced, tricky part of Kafka. I don't know much of it in detail, but I can tell you the following fairly confidently. By using Kafka in this multi-partition mode, you're effectively trusting Kafka to balance the load across your consumers. If one of your consumers is slow and it's behind by a lot of time, I think Kafka would realize that. I mean, I'm pretty sure Kafka would realize it and reroute the messages to another consumer of your consumer group. I'm positive you can change its behavior by tweaking its parameters, both in terms of Kafka internal configuration and in terms of consumer settings on the fly when you establish the connection to consume from certain topic. But I'm almost positive that unless you are deep in the weeds, by using Kafka the intended way, you're supposed to not have to think about this. That's what Kafka is supposed to handle for you.
oh, okay, I got it. Yeah.
So yeah, if you find yourself trying to route multiple partitions to the same consumer, I'm going to postulate that it most likely happens for one of two reasons: A, causality. You want to make sure Alice account creation, Alice account credit end up in the same consumer. And B, performance. You may have non-homogeneous data in your topic, and some messages take a lot longer to process, and somehow they are misrepresented in different partitions. So some partition is just a lot slower to be processed. Both are real issues. And yes, by the way, you can define the partitioning key for Kafka. So in many cases, you would use a random number so that the sharding of messages into partitions is random. But in many other cases, you would say, oh, I'm gonna postulate which partition to go to. And then you have this hotkeys issue, where suddenly one partition can be a lot broader, a lot bigger than the others, because the hotkey is there. And then that's when, of course, your network connection could be slower. Maybe here, like 0, 2, and 3 are fast. 1 and 2 is saturated, deteriorated. Maybe consumer 2 is in different availability zone in Amazon, in AWS, and then your router failed. A lot of things can go wrong. And again, my assumption is that if you were to use Kafka in this way, you're supposed to trust its own mechanisms, its own internal mechanisms. If you want to tweak them on a Kafka level, not on your software level, because things will go wrong if your smartness will interfere with its smartness. And the final advice is, if you feel like this is important for you, maybe you shouldn't use Kafka, because that's effectively what AMQP allows you to configure to some degree. Make sense?
Yeah, thanks, Dima.
Again, obligatory disclaimer, I'm not a Kafka expert. I know these things fairly well, but don't quote me on them in the real life big decision-making points. My approach is to talk to people who know this better and to experiment, like set up POCs and experiments. But from what I said so far, I'm fairly confident that's the case. One more thing I have to say. There are tons of message queues out there. Rabbit and Kafka are certainly not the only options we have. The big disclaimer here is that in addition to Rabbit and Kafka and other open source-ish or closed source solutions that you can deploy yourself, there is an emerging trend of cloud-first queues. So if you were to remember one thing from this event, but this one thing can contain two parts, it will be the following. First, there is no single dichotomy, single dimension along which you can compare different message queuing solutions. But if there's multidimensional space, the principal component, the principal dimension would be Kafka versus Rabbit, Kafka versus AMQP. But the second principal dimension, the second most important dimension is, are you bound to use a solution that you deploy yourself? Or can you use the cloud-native solution from your provider? Because chances are Google pops up in GCP or Kinesis or SQS from Amazon could work for you. I'm deliberately not talking about the cloud solutions in this episode because A, I'm not an expert, and B, I think it's, even if you never use Kafka in your life, I hope that everything I said so far was useful enough to learn, even if you don't need to use this explicitly. But yeah, just if you remember one lone thing from this event, remember that the first dimension, the top dimension, is Rabbit versus Kafka, but the second one is you deploy your own code versus you trust your cloud. With this being said, there are tons of other solutions, and again, I'm not an expert in Kafka and in Rabbit, so I'm clearly less of an expert for other solutions. It's just in my experience, first of all, it almost always gets to Kafka versus Rabbit in most cases. Second, we have to discount point-to-point solutions, such as ZeroMQ, not because they're not useful, not because they are not important. I just don't think they are system designy for our intents and purposes. My goal for this meetup is to articulate how to build complex things from simple components. And the decision to use, let's say, ZeroMQ versus gRPC, what's a gRPC channel versus a plain TCP socket, yes, TCP, not UDP. The decision to use one of these three would not be a system design decision. It would be an implementation decision for your particular channel between 2 points. So I'm not saying ZeroMQ is simple and it's not worth talking about. I'm just saying it's out of scope for us right now. We're talking about this distributed multiple boxes, multiple arrows, databases, caches, message queues. And in this setting, message queue is largely what Kafka and Rabbit mostly cover in terms of applicability. So there are other solutions. In my experience, they would be either not popular enough to talk about in a broad setting, or they would be close to either Rabbit or Kafka in their design principles and their design philosophy. So again, not saying we've learned everything by talking about these two, but I do think we cover a decent chunk of this space. This was it for the part where we talked about Kafka and Rabbit, and the remaining part, a couple of slides, is about the leeway into the actual distributed task queue problem. So maybe if there are questions, that would be a good time. Yeah, go ahead.
Yes, I'm just wondering, so is there something in AMQP protocol which doesn't allow us to implement the serializability or the reliability and all the stuff which Rabbit doesn't have? Or it's more related just to the implementation of the Rabbit, and we can do this via on our hands, our own kind of some implementation of some message queue?
Wait, these are two different questions. AMQP is a protocol. It's an open standard. It's a convention like HTTP. Rabbit, I think for the Rabbit part of your question, the answer should be straightforward. Rabbit is effectively the clever way to leverage Erlang at the Erlang virtual machine. So you have to assume that each event, each message lives in its own micro thread. So introducing any causality guarantees there would be not even hard. It would immediately take you out of the realm where this virtual machine of Erlang is effective enough. You would have messages internally talking to each other in order to establish certain ordering conventions. So just assume they are independent most of the time. If you want to have some causality requirements, you can think of a custom broker that is effectively after this Erlang magic happens. It could be a custom component, or it could be already implemented as part of the Rabbit's brokerage implementation of AMQP. But it would by design not be, by definition, by construction. It would not be as effective and as reliable as what Rabbit truly offers you when it comes to this intersection, the sweet spot of AMQP and Erlang. So for example, durability, persistence, storing things in memory, I'm almost positive it will have to be, I wouldn't say it's independent per message. I'm pretty sure it writes blocks to disk, but I'm fairly certain it's designed to treat messages as, or have this few hundred messages or few million messages. Let's persist them somehow so that we don't lose them. If you were to introduce ordering constraints there, like sequence ID on previous message index, like git commits, commit has a previous commit, you could do it, but it would break the logic of the very Rabbit Erlang machine. And of course, if you need to use, so I'm thinking out loud here, if I were to approach the problem as you just postulated, I would have my own router, right? I would have my own broker node. And in order for this node to work, you would need to talk to some external data store, such as Redis, or Cassandra, or Dynamo, or Memcached. Just remember that since Rabbit is Erlang, it's a lot harder to build Cassandra in Erlang than to use Cassandra. It's a lot harder to build Redis in Erlang. It's just not the language it's designed for. So logically, you probably would do better if you have this custom broker component that uses Redis as this caching layer. And I would not bet on Rabbit itself having the correct implementation. No, correct is of course the wrong word. I would not bet on Rabbit itself having the implementation that is efficient enough that compared to what you could do by just cleverly using Redis out next to your, you would put Rabbit, you put your own broker node, and you would put Redis next to it. Your broker nodes could be sharded, of course. I cannot possibly, for any non-standard use case of AMQP, I'm fairly positive your design would be more effective just because it's not trying to break the pattern of Erlang. That's at least my instinct so far.
But I was mostly kind of asking about maybe not really kind of how to patch the Rabbit to make it in ordered or in some other way, but more about, can we build the custom solution? We will be kind of having some guarantees of Kafka, maybe not all of them, but it will be, for example, having the order, and at the same time it will implement the AMQP in the protocol, and we will have all this stuff for the routine, which is not in the application code.
You would certainly enjoy Martin Kleppmann's talks. The TLDR would be that so strict ordering is the problem that is fundamentally equivalent to distributed consensus. And Erlang's VM is explicitly arguing that each execution is not machine dependent. It can be spread around everywhere. But if you have this AMQP broker that decides where should messages go, you can think of this AMQP brokers as an internal, elastically shardable bunch of machines or threads or whatnot. And the only reason they are so effective within Rabbit is that they don't need to talk to each other, or at least they only talk to each other in some large groups. If you want to order messages one by one, then for each individual message you would need to agree with all the other nodes. And agreement is really hard in the distributed world, even if it's a single machine, even if it's just multiple threads. Agreement is really hard. So I can, as long as you can afford some partial order, you might be good to go. But if you need total, so partial order is actually a good idea. Like you respect causality, your order of messages is like a topologically sorted set of all the messages. So whatever you depend on is guaranteed to come before certain. Whatever the message X depends on is guaranteed to come before X. But there's no single unified replayable order. As long as you're fine with this, you might be able to use Rabbit in a clever way, like cluster by correlation ID of the original message, route to individual internal brokers this way. I'm almost positive solutions like that exist. But as long as you have this financial ledger, where you have a strict order designed to be replayable, trust me, you don't want to even try to use AMQP for that. That's at least my instinct. Even if AMQP has extensions for that, I would not be surprised if those extensions are using Kafka's internally or Kafka IDs internally. and like rewriting their own append-only log files, even temporarily, just to make it effective. And maybe even doing literal actions between these broker nodes on the fly, again, internally.
Thanks.
Yeah, Tima, just adding on to that. So since Kafka guarantees us order, and a single topic can have multiple partitions and be spread over multiple machines, does it use some kind of distributed consensus to guarantee order across partitions spread across machines?
That's what it does not do explicitly by design. Kafka does use literal actions, but there are three things. Let me lay them out in the right order. So Kafka does use literal actions, but then if you have multiple replicas of a partition, these replicas are identical for durability and persistence reasons. So there are actually three levels of abstraction. There's a topic, there's a partition, and there's a partition replica. Kafka does use literal actions explicitly to make sure that the data is replicated into however many places you want it to be replicated to for data durability reasons. Kafka does not try to have partitions talk to each other. That's the very idea of partitions, to maximize throughput in a horizontally scalable fashion. Which honestly, I think I wouldn't call it a mistake, but I think it's a very limited design decision. It's a longer conversation why Kafka as a company, as a product, has not made any changes there. I don't want to get into this today. But it's just, I think you've hit the nail here. That's exactly the limitation that Kafka does not offer and will not offer anytime soon, because that's exactly the design decision the Kafka team has made a long time ago.
So the order guarantee is per partition?
Right, yes.
Okay.
This might be going a bit off the topic, but I'm currently writing a design doc, which I think I'll publish sometime soon, maybe even this weekend, on event sourcing, on the proper event store and event sourcing design. And if the topic of synchronizing partitions concerns you, the standard solution which is used everywhere is called heartbeats. It's like persistent keep alive. Imagine you have a single authority, like magic machine that doesn't die, or a small literal letter cluster, that publishes to all the partitions the message that the world time has increased from second X to second Y. This would be once per second. And since Kafka is performant, this can be many times per second, or less frequently if you need to. In this case, you can artificially, on your subscriber group, you can artificially synchronize with some external heartbeats. So you can say, I'm going to process this second, then wait. Maybe I could prefetch something, but I'm not going to process them. Then I process the next second and wait. And then within each second, within each slice, since each partition would have its own records for second A ended, second A+1 ended, within this slice, it would not be vertical slice, right? It would be like distributed across partitions in different places, because partitions are not going at the same pace. They can like one can overtake the other, and things would happen in weird ways. But if you have those heartbeats, you can at least simulate these ordering guarantees by reordering everything within a single heartbeat. You could use some server time as a secondary sort key. You can use partition index as a secondary sort key if you don't care about 1 second drift. And you can later introduce your own causality requirements, topological sorting on top of this. It's a fairly advanced thing. I've tried talking about this to many people in the past 10 years, since I'm in this field for a while. If this is really what concerns you in your project, in your day job, chances are you either have somebody who really understands this well, far better than I do, or the team is doomed because people would make wrong assumptions and this would not fly. That's my current understanding of the world. All right then. Yeah, I assume they should answer the question. Thanks. All right. We should be able to cover the task queue part fairly quickly as the setup, as the framing for the second part of this, to be honest, for the next episode. So before I talk to you about functional requirements, since it is an educational episode, obligatory disclaimer, of course, I'm still undecided in my head. What's the right moral stance on interview preparation? I'm deliberately against public episodes that help you prepare for an interview question. But still, I'm fully aware that quite a lot of you guys found this because you need to prepare And I hope that in your efforts to prepare, you'll learn some fundamentals too, which should help you make our world a better place. So for the distributed task queue, it appears surprisingly often in a huge spectrum of interview questions. In fact, I know it's a common perception fallacy, but as I started working on the slides and thinking of what should put into this episode, I started seeing it everywhere, more or less. So one of the canonical examples, I think, is I put Vase and Nearby Friends first because they're more popular. But people are asking more and more, I ask it more and more, how would you design, like you open a virtual whiteboard, Miro Whimsical, and if you have 100 people there, you see their mouse pointers. How to design the system where all the 100 people can see all the other 99's people mouse pointers moving in near real time. Of course, you can lose the data. Of course, you can, like, no single pointer must be at 60 FPS. It could be 15 or 10 or even 3 if it's overloaded. But it's just such a standard problem for Rabbit, and it's such a major bummer if you have to design something like this and you don't know what Rabbit does. That's pretty much one of the easiest examples. The web crawler, it's presumably a pretty simple question for interviews these days, though there are multiple queues inside it. And the crawl queue is by itself a tricky question, especially once priorities come into play. So once you have to recrawl certain pages more frequently than others, the majority of the web crawler problem is effectively about managing the crawl queue. Your workers just crawl the pages. You probably want to have an extra queue between the crawl phase when you get the HTML and maybe JavaScript, CSS, and then you have a second cluster of workers that parse these pages to extract the outgoing URLs to be added to the crawl queue. So between these two components, you may have to have another queue. If it's an indexing job, for example, to update web search index, it's not the only use case of web crawler, but it's a common one, probably the most popular one. You have the queue to notify those index of pages that have this new version of the page. You may want to update your index there. And then those indexes can be real-time or not real-time, so that's more and more queues. Some of them can be Kafka, some of them can be multi-partition Kafkas because the order is not important. But web crawler is all about queues, surprisingly. Ticketmaster itself, a really common problem these days. Ticketmaster itself is about properly using RDBMSs for transactions, but you do want to update, like if I'm looking at the page of a certain show, I have the seat map, and I expect some seats to be green as available, some would be, I don't know, gray or black, booked out. Some are currently being booked, but they may or may not become available to me. Some are cancelled, so I canceled my booking. If 1,000 people are looking at the same show page from their browsers, chances are I want these pages to reflect updates in some real time without them refreshing the page, which again, you can just say, I'm going to put an HTML refresh or more like a JavaScript reload via like JavaScript code. I'm going to re-request the seed map. You could do it, but fundamentally it's a data queues problem. And of course, there's an advanced use case of Ticketmaster where you have this queue, the wait list. If the show is super popular and they release seats slowly, or you have to wait until somebody hopefully cancels their order so that you can get a seat to that show, that's entirely a message queue problem. So that the queue itself is simple, it's on the backend, but delivering this queue status to every single user so that you see in your screen, you're number one on the queue, you're number two in the queue. You probably don't want to count one by one for millions of users. So you would say something like, oh, you're in the first 100, you're in the second 100. It's a perfectly designed queue problem that is super hard by itself unless you know how to use queues. Uber and Lyft, when you're requesting a ride, technically it's a task queue because you need to decide which potential drivers could be a good fit for you under multiple constraints. And if you don't send the ride request to only one driver, I mean, you do send it to one driver, but if they don't confirm the ride, probably send it to more drivers so that the user doesn't have to wait for all this time until the first driver decides yes or no. So fundamentally, it's largely like the part where you request a ride from a ride-sharing app is largely this task queue where what you need to send out is the ride request, and you need to decide which drivers to send this in which order and with which delays. If you need to update your UI in the real life, in real time, for example, I'm looking at hotels on Expedia, see if some new hotel just canceled. If a booking was just canceled in a hotel I looked at 10 seconds ago, chances are you want to notify the user, hey, while you're here, that hotel you just looked at, it was fully booked, now it's not. Task queue. If you have a hotel you like that is offering a discount, and this discount just started, notification makes perfect sense. If you close the app, but then open it again and start looking, well, that's a synchronous use case, so simple. But still, you probably want to notify the users when they're not opening the app. Hey, you may be interested in these hotels because you haven't booked anything yet. So surprisingly, queues again. When you need to update the UI, I think it's the same problem as with hotels. But let's say it's Facebook and there is an earthquake. You probably want to notify me that my neighbors are okay, and you might want to ask me, hey, there's this box you can tick that I'm okay. Would you like to do it? Who to send this message to? Task queue. And I've used these questions twice, the last row of the slide in my own interviews. How would you design the runners for CI/CD actions, like GitHub actions? It sounds simple, but it's so painful. It's effectively a queue problem by design, right? And it's incredibly hard to design as well, so that it scales and doesn't cost us tons of money. The bottom line, task queues surprisingly appear in multiple interview questions. And yeah, obligatory disclaimer, interview grade design is absolutely not the same as real life design. Happens all the time. But assuming we also need to pass interviews from time to time, we need to know how to draw things in standard boxes so that we leave the impression of the people who understand the big picture problem statements. So what I will do here, instead of solving the problem yet, since we're just setting the table, I'll talk to you about how I asked this task queue question in isolation. Fundamentally, again, talking about interview prep now, I would imagine good candidates to ask me questions along the way and clarify these things by themselves. So I wouldn't just outline, hey, here's the spec, read it, and then solve it. So even though this would already help you a lot, because I'm gonna highlight the most important areas to cover. So the way I ask the task queue question is I talk about the image and video editing service. So you have the images and videos already within your service. They are uploaded to you by the end users. They are in some file system. You don't need to design that. And the users can request certain operations on these videos. Some are on these videos and images. Some are super quick and simple, such as download this PNG as a JPEG. Well, you need to re-encode the image, but still, it's a sub-second operation. It's super quick, but chances are you don't want it to be done by the same node that received the request, like from the web browser. Some operations are super slow. I have one video of a concert, I don't know. I have 4 friends recording the same video from behind my backs. You could use these 4 videos to make my videos sharper, using some machine learning and stuff like that. Chances are I can offer this as a premium feature for my customers. So it's a task scheduled by the user, which could take hours or days to complete. And yeah, it's also a task that is subject to be put into the queue and then executed by some worker, maybe in chunks. Some tasks are multi-step and they have external dependencies, such as, again, manual review, manual grading. Maybe you want your video to be published for kids, for which the requirement is we need to make sure that our process confirms it doesn't contain anything that is not safe for kids. And this process is manual. Maybe you need to send it to 3 people, and at least 2 of them should confirm that it's okay. Again, manual process. The task should be in the queue, pending. Ultimately, maybe sent to other people if these first 3 you sent to don't respond in time. It's still a task queue problem. And some tasks have external dependencies, like on YouTube. If your button is upload this resultant video to YouTube in this quality, send me back the link once it's uploaded. So I expect to get an email that, hey, your video is uploaded, take this, follow this link. So I'm going to postulate actually that the machines, the nodes, the servers that run these actions are of course not the ones that receive them from the end user. So I have this front-end load balancers clusters, of course, front-end load balancers cluster. I have the application servers for the web pages or the mobile app, whatnot, and I have some internal, like fully in the backend bunch of machines that can do all these tasks eventually. So I usually ask people to not worry about who owns these machines. I just claim they're outside. If the candidate is strong, I would also talk about task priorities, which can be hard. I would talk about custom retry policies and task dependencies, which is even harder. And I would talk about monitoring the workers so that I could notify, hey, the queue is getting bigger. why don't you add more nodes because we're losing money if we don't do things quickly enough, and vice versa. And yeah, I'm not saying this is all important. It's just how I would approach this if I'm asked this question and I need to outline the functional requirements. Or that's what I would tell the more junior candidate who just asks me for more and more requirements. And then, of course, for NFRs, non-functional requirements, I want my queue to be available. So it's certainly going to be multiple machines that run my queue. If some of them die, I expect the queue to still work. It has to save the data to some hard storage, like disk drives, so that if somehow all the machines are down, whatever happens, I can still resume from my own previous state. People forget about the task status API. I probably want to have some, it's a sub-problem, of course, it's not directly related to the queue itself. But if my tasks have IDs, I want to have some way to tell if the task is completed or not. Not just, I'm going to send you an email once it's uploaded to YouTube, and until you didn't get this email, assume it's not done. I probably want to have some status page where I would be told, oh, you've filed 10 tasks in the past, I don't know, week. This one is still pending. These are done. This failed because whatever, change it. Back pressure, we talked about it for a bit at the beginning. I don't want the queue to grow infinitely, indefinitely. I want to maybe at some point tell the users, hey, the queue is full, try again tomorrow. It's just not feasible for the business to assume I can pile up tasks for the next year or so. The beauty of this problem, and the curse of this problem too, is that it doesn't have to be exactly once. In fact, you can make mistakes in both directions. Losing the tasks once in a while is acceptable. You can just expect the users, like if the user of 1 million or of 10 million would say, oh, this service lost my task, I had to resubmit it, it's not going to be the end of the world for your business. Unlike financial situations where the ledger is there for a reason. And if you process the task twice, in most cases, you just waste compute resources. Again, no big deal. I want it to be the queue that loosely resembles FIFO, first in, first out. There's a famous, pretty common failure mode that people start talking about, like Kafkas after Kafkas, like second order Kafkas with partitions per workers after third order Kafka with the actual task queue. But if you pre-assign tasks to nodes, and if one node is slow, the tasks that are queued after the slow node or after the slow task for this slow node are now pending. So you can have 100 workers, 99 are idle, and one worker is doing a 10 hours job. And suddenly some other tasks that could be handled by the other 99 workers are stuck in the queue after this 10 hours job. So you need to reshuffle them between workers if you queue them in a per worker queue. So per worker queues are not the best solution in the long run. I need some monitoring, detect installed workers, and ideally I should be able to utilize all the workers 24/7. If I don't, I'm losing money. I'm not solving the problem correctly. And last but not least, I would accept the answers about cloud primitives such as AWS Kinesis, but I would politely ask the person to talk to me from the first principles like we just did. Again, my bias, fully aware of that, but I think it's useful to be able to think in these terms. Yeah, I think it's a last slide with content. So to frame the problem for the next episode, to begin solving the actual problem, you need to make two observations. One is that when everything is just working fine, it's working fine. The issues begin when something is not working fine. And there are two major failure modes. One is you're almost never in a queue full state. You always process stuff fairly quickly, but then suddenly you have a spike and you need to persist the task somewhere. That's where if you were using Rabbit before, maybe for my tasks of this image and video resizing and changing, editing, altering, Rabbit could work out of the box. But at some point, suddenly you're on TechCrunch or in Hacker News, and the queue is days long. You don't want to lose these messages. You will lose your loyal customers. So suddenly your Rabbit has to persist stuff. That's one failure mode where something more like Kafka is probably desirable. The other failure mode is everything dies. You need to persist your tasks. Maybe you want to restart the whole thing in a different data center that is cheaper or more powerful. If your queue is tied to one data center or one cloud provider, you're screwed. Like, what if tomorrow I want to move from, I have an emergency. AWS shut me down because I violate their policies. I need to move to bare metal or GCP. How do I do it without losing all the tasks? If the tasks are stored in some weird place that I don't fully control, like Rabbit's in-memory-ish store, it's a hard conversation. So that's the first observation, that I kind of have failure modes for both Rabbit and Kafka. So I'll need to have a mix of those, or design my own primitives that would leverage parts of them, or design my own thing without using any of them. I just need to explain carefully what these primitives would be. And one thing people often miss is that you would have 2 or 3 APIs to design. The API which pushes tasks to the queue is one API. It's more like user-facing, even though the user is not the end user, but the service that talks to the end user. That's why you have idempotency tokens. That's why you define retry policies. That's why you set dependencies for tasks if you have them. Priorities too here, part of run policy. Then you have a second API through which your actual workers who would perform the tasks talk to the queue. It's okay, I think, to say, hey, I have this single API endpoint. Give me the next task to perform. That's a good start. But then what if you fail? Do you have heartbeats? How do you make sure there's not double processed, or at least not double processed frequently enough? Again, that API by itself is worth designing carefully. And people often forget about the third API, check task status. Because, as I said before, maybe it's not enough for you to receive the email about, oh, your video is currently on YouTube. Maybe I want to be able to see in the tasks submitted list, green, yellow, spinning, still running. That's what I think constitutes this problem, because after all this is covered, it's going to be about the diagramming and whiteboarding, the actual design, which we'll do next time. I think that's it.
Tim, I have another question. So in one of the previous slides, you said that you should ideally design in such a way that the worker should be the bottleneck and never the queue. But is it always possible to design like that? Or is it desirable to design like that? Because there could be a flurry of data incoming, and it could never be possible to make the queue very small when there is loads and loads of data incoming, right? So it's only desirable to do that, right? So what you mean by that is the workers should be scheduled to work on these tasks as soon as possible. I'm not able to hear you. I think you're muted.
Hard muted with my switch. Sorry. So what I mean by that is the workers should not be idle, because we are losing money if the workers are idle. That's as simple as that. Now to your main question, or do you have? I'm not sure you finished the question. You just told me I'm muted.
Yeah, no. My point was it's only a desirable property of the system rather than an achievable property, because in times of bursts of requests coming in, the queue will eventually become a bottleneck. But I get your point that
the bottleneck as in, so the queue become bottleneck once we have phrasing it better. If the queue handles back pressure, it's not a bottleneck. The queue is the bottleneck if it's overloaded and suddenly scheduling new tasks times out. It's okay for the node that sends in the task to receive, sorry, I'm busy, try again later. For the user to see the message, hey, our queue is overloaded, try again tomorrow. That's fine. What is not fine? What is not fine is that the queue suddenly begins serving requests with, I don't know, 10 seconds timeouts, and some of them are failing. It's okay.
So using back pressure, you push the request back to the clients, but not accept them and then take an inordinate amount of time to process them. That's what you mean.
It's okay. Let's define the demarcation line here. It's okay for the task to be in the queue for a long time. It's a separate question. Shall we notify the user, hey, your task is still pending in the queue. Do you want to cancel it? Or do you want to upgrade to premium to make it run faster? That's fine. The not fine part is that you cannot push a task to the queue. The API, the front-end API for your queue, which is the API by which new tasks are inserted. This API should be running under its own SLAs, fully available, consistent, reliable, even if the queue is suddenly 100 times more full as you expect it to be, than you expect it to be. The fact that the task and the queue are no longer taking 10 seconds, but 10 days because the workers pool is exhausted and they are slowly crunching to the tasks, that's not a failure mode for the queue itself. It's the failure mode for the business. We need monitoring and alerting for that. We probably want to add machines for processing power at workers on the right-hand side of this diagram. But it's not the failure mode for the queue itself. The failure mode for the queue is if publish on a task suddenly is the call that fails on this chain.
Okay.
I can probably answer it in more simple terms. For Kafka, it doesn't matter how many log files we have on disk. As long as the disk is not full, adding a new message takes order of one in loose terms. For Rabbit, since messages are mostly in memory, it can start swapping and persisting. Once Rabbit has used all the memory you allocated to it, its performance deteriorates to some degree. That's what I want my queue to avoid.
Yeah, now I understand. Yeah.
Now to answer the first part of your question, if the workers are by design stateless, and they are, it's a lot easier to add workers than to add nodes to the queue. So if your queue capacity, if your queue throughput, not the storage size, but the SLA of the input API, you can say I design my queue so that I can handle up to 10,000 workers that perform tasks every second or so, and I can accept tasks at 100 QPS, 1000 QPS at peak. That's fine. And then somebody comes to you and says, you know what, I want to use your queue in a different project, where the tasks I pose to the queue are not manual review tasks, but they are like financial transaction trigger tasks. So I'm not happy with 1000 requests per second at peak. I need to have a peak of 1 million per second. So it doesn't load the queue yet, it loads the front-end API for the queue. So we're talking about the SLA of the part where you push messages to the queue. Now you could say my queue is scalable infinitely horizontally, and I can add machines to the queue itself and to the queue front-end API part and handle 1 million per second. That's fine. You could design such a queue. But generally, workers are totally stateless, so they're super cheap to add. A few button clicks, some workflow in Amazon or GitHub, some SRE button, even automated if the queue suddenly is larger than expected. Done. The magic happened. Elasticity at its finest. Cost-effective, performant, wonderful design. You probably don't want to scale the nodes within your queue automatically. There's too many things that go wrong. It's a far more manual operation. It could be delicate and sensitive, and you can lose data. So that's why it's more important to talk about utilizing the workers effectively, because then you can always maintain the number of workers exactly at the number you need, so that it's cost-effective and still performant. That's more important to mention as a requirement to the problem, compared to making sure your own task queue can be scaled. Because quite frankly, in most cases, the queue would fit like 3-5 machines in your case. So you don't need to add more machines for performance. So in terms of interview, it's just about durability, just about availability, that if one of your queue machines dies, the other two can handle the load. So you don't really need to scale the queue unless it's a super high performance use case. But the front-end API, through which you insert the tasks into your queue that you design, should behave according to its own SLA, which is tight enough in terms of average and peak requests per second, task push requests per second.
Yeah, I get it.
Great. Thank you.
I have some small question also related to the requirements. Don't we have anything there for like a DLQ, for example? So if our workers haven't handled this message properly, there is a bug from our, I don't know, intern came to the new team and went to bug in the workers. So it looks like we need to store somewhere the message from the client and to replay it after we fix it.
I removed 2 things on these slides, specifically to make them shorter. The dead letter queue, DLQ, as you just mentioned, and something else taken out. So yeah. And handling tasks of death. You should not be able to push a task that kills your system by mistake with a retry policy of retry forever, and then have it kill all your workers in the next few seconds. So this I think they have a lot more to do with the actual task queue as opposed to Kafka versus Rabbit. And I tried to. So maybe I screwed up the demarcation line between the first part of the episode and the second part of the episode. But I was trying to keep the today's part more Kafka and Rabbit related, and then tackle the task queue questions in the next episode. But yeah, DLQ is important, dead letters queue. Manual attention required because this task has killed too many of your workers. It has failed and you may want to do something about it. All right, shall we call the Rabbit plus Kafka episode concluded? Thanks everyone. See you next time.